All right, everyone, we are going to pick up with where we left off on 7.6, solving rational equations. Last week, we looked at simplifying complex fractions. We looked at two different methods where we would separate the numerator from the denominator as like two different problems. And then we would evaluate each. And then once we had a fraction divided by a fraction, well, now we could just keep switch flip. So we're very familiar with that from our extensive exposure to factoring and to fractions. So what we're essentially doing with this solving rational equations is we're sticking with this idea of you have your problem and you want to cancel fractions, which is why we use the LCD when we were looking at complex fractions. I know I said fractions a million times. We are going to cancel them out in order to help us solve. The only issue with rational equations is that we have to be careful with something called extraneous solutions. And essentially what we mean by that is if you have an equation with variables in your denominators, we have to be careful not to create any zeros, right? So for instance, and you can shout out the answer, what is any number divided by 0? What does that give you?
0.
Punch it in. Punch it in. Do pick any number and divide. Error. You said error. Mathematically, what would error be synonymous with?
Non-real.
Non-real or undefined. Okay. So you cannot take a number and divide by 0. We can prove that. If you took 7 divided by 0, you would see that in your calculator, right? So this is just a reminder that you cannot have zeros in your denominator. So that's one thing we actually have to be careful of. And that's only if you have a variable in a denominator, okay? But let's take a look at a bunch of these. Yes, it's fractions galore. So hopefully you don't, panic or anything like that. I just want you to move through this at a nice pace. So don't overthink it. Let's take a look right now. All right, how to solve rational equations. Like I said, first things first, you're always going to factor the denominators in order to find your LCD, just like we did this entire unit so far. You're then going to clear the fractions by multiplying every term. You don't get to pick and choose. Every term in your equation must be multiplied by that LCD, okay? And then you're going to solve the resulting equation. You always want to check your answer in case you have a solution that makes that problem undefined. So you want to just clarify that you don't have any extraneous solution. Okay, let's take a look at example 13. Someone shout out, what is your LCD?
4.
Yes, 4, absolutely. Take every term and multiply it by 4. Place each term in parentheses. In the first term, what happens? Shout it out.
4's cancel.
Beautiful. 4's cancel. That leaves you with x. Someone else, in the second term, what happens?
One over 2.
Well, tell me what happens here.
We divide 4 and 2.
Okay, good. So that means 2 goes into itself once and 2 goes into 4 twice. So that leaves us with 2 times 1, which is just 2, right? Be careful with your fractions in terms of what's going where. For the last one, what happens here? Someone else shout it out.
2 goes in the, we cancel the 2, it goes into the 4 twice, and we have it leaves us the 2x minus 1.
Yes, with the parentheses. That's exactly correct. So you're left with the 2 and the x minus 1. We are going to leave the parentheses because 2 acts as a coefficient, right? Which means we're going to have to distribute before we actually drop the parentheses. So we have x plus 2 equal to 2x minus 2. Luckily for us, this is a linear equation, so we can solve this super quickly. I'm going to start by subtracting x on both sides. And that's going to leave me with 2 is equal to 2x minus x is x minus 2, and then I'm simply going to add 2 to both sides, and x is equal to 4. That is my solution. I want you to notice in this case that I don't have any variables in the denominator, so it's safe for x to be equal to 4. There's no chances of providing any zeros in our denominator. If we do have variables, we want to double check, okay? And what we're actually going to do first is determine what solutions would result in an undefined equation. First things first, 0 divided by 2 is 0, but 2 divided by 0 is undefined. Make sure that you note the order of your terms. The second there's a 0 in the denominator, that's a problem. Okay. Now, we want to figure out when this happens, right? We want to figure out what my restrictions are. So I want to break this down as easy as I possibly can. The only time an expression is undefined is if the denominator is equal to 0, right? So if I want to figure out where it's undefined, I need to figure out where the denominator equals 0. So let me show you what I'm going to do. I'm going to take this denominator, x plus 2 times x minus 2, and I'm going to set it equal to 0. You're probably thinking, wait, can't you just divide out x minus 2 and get rid of it? No, because the point of this is to figure out where the denominator is undefined. So what we do is we focus all of our attention on the denominator. As far as I'm concerned, this numerator is blurry, right? I don't even see it. It doesn't even exist to me. It's just like blurry letters and numbers. So you're just focused on the denominator here. We're going to take each factor containing a variable, set it equal to 0. When we do this, we recognize that when x is equal to -2 or when x is equal to +2, let me get rid of this, I didn't mean to write that. Our denominator will result in a 0. So what that tells me is that no matter what, if I were to, go ahead and solve this equation, let's say we're equal to something else, I know for a fact that x cannot be equal to -2 or +2. Because that's where it would result in a 0. We can also think about this logically. -2 plus 2 is 0. 0 times -4, that gives me 0. Well, a number divided by 0 is undefined. So I can never have an answer where x is -2 in this case. If x is +2, 2 plus 2 is 4, but 2 minus 2 is 0. 4 times 0 is 0. So that means we can never allow x to be 0 in this one, in this expression either, okay? If, again, we were solving it. When you're not solving, it doesn't matter because you're not finding solutions. But right now, we're just practicing on identifying where those undefined values would be. Take a look at your denominator here. Again, your numerator doesn't even matter. Pretend it's blurry, okay? So you're going to take your x squared plus 5x. You're going to set that equal to 0, but recognize that because it's a polynomial equation, we want to factor. What's my first step of factoring here? Does anyone see it?
X.
Beautiful. You're going to factor out that x, it leaves you with x plus 5 is equal to 0. What are my two solutions here? X is equal to?
0.
And?
-5.
Beautiful. X is equal to 0 and x is equal to -5. Just to verify this, I'm going to write both factors equal to 0, and I'm simply going to write out the two solutions. So the restrictions are in this case that x cannot be -5 or 0. Notice that I am writing my restrictions in ascending order. It doesn't matter. You don't have to worry about that. Our last one is x squared plus 4 is equal to 0. What do you know about this expression right here? Talk to me.
Squares.
Okay, so you're seeing squares. This is true. What was the factoring technique called?
Difference of perfect squares.
Okay,
Mm,
difference of perfect squares. Is that the case here? Is this the difference of two perfect squares?
No.
No. Believe it or not, this is that expression where we can't factor it,
Mm,
right? We can't factor it. I want to prove something to you. If I subtracted 4, can you think of a number where we square it and we get a -4? Is that possible? No, right? No. -2 times a -2 is a +4. 2 times 2 is a +4. So there are actually no restrictions in this case. There is no value that when you square it will be equal to -4. So we're actually safe in this case. That's all essentially that we're looking for. When we talk about, is this rational expression defined, like where would it be undefined? We could say, okay, the restrictions are as follows. You look at the denominator, set it equal to 0, of course, factor and solve. Those values, if you do get any, those values will be the restrictions, right? Let's turn the page and keep going with this idea. Okay. The very first thing I want us to do is I want us to carefully look at this particular equation. We now have an equation. 4 minus 5 over x is equal to 7 over 3. Out of curiosity, what number can x not be? Just by looking at this, what can x not be? What number is this not allowed to be?
0.
Yes. So my restrictions are that no matter what, x can't be 0. Excellent. If x were 0, we'd have an undefined fraction, which means my problem is undefined. So that's something to think about. Let's go ahead and solve this. Summer, what is my LCD in this case? What is your LCD?
Would it be 3?
What's your other denominator?
X.
Good, put them together. 3x is your LCD. You want to,
Okay.
yeah, you want to keep all of those together because that way you can actually cancel out fractions. So our LCD is 3x. We're going to multiply every term by 3x. And this is kind of a recap of what we were looking at earlier in this unit when we were adding and subtracting rational expressions. So this gives us 3x times 4, which is 12x, minus, notice here that my x's are going to cancel. They're going to divide out, which is exactly what we wanted. So we're left with 3 times 5, which is 15. For our last term, notice the 3's are going to divide out this time. So we're left with 7x. Okay. This is awesome because it's linear, so we can essentially solve no problem. I'm just going to bring the 12x over. That leaves me with -15 is equal to -5x. And then, of course, we are going to divide by -5 so that we could get x completely by itself. And we find that x is equal to 3. So we have our solution. When we write our solution set, remember that that refers to your braces. They're back again. Place your solution in a set of braces, the little squiggly bars. Cool. As we move through this, please stop me to ask questions if you have any, okay? Don't be shy about that. I want to make sure that you're okay. Let's take a look at part B. Look at the fractions carefully. What can X not be this time?
0.
Let's test it out. If X is 0, 0 minus 5 is -5, so that's okay. I can have a -5 in a denominator. Try that
Can't
again.
be 5.
5 is correct. Our restrictions is that X cannot be 5. If X were 5, 5 minus 5 is 0. That's a problem. So go back to this idea of let's set the denominator equal to 0 to figure out where the restriction is. And that is that X cannot be equal to 5. So if we solve this and we find that X is equal to 5, we would say, no, sorry, that's not an actual solution. So there would be no solution. It would be extraneous. Okay, I love it. So far, so good. I'm going to call in someone to provide the LCD in this case. Let's go at Nung. What is the LCD for this particular problem?
It would be 3 and then X minus 5.
Yes. Notice that Nung included both of those denominators. So when she says 3 and the X minus 5, she means the following. Go ahead and put everything in parentheses. She means the following. 3 times X minus 5. That is the LCD. 3 times X minus 5. 3 times X minus 5. All right, it must be a combination of the two. All right, for our first term, we have 3 times X minus 5 times 2. I'm just going to write it as, we know 3 times 2 is 6. So I'm going to write it as 6 parentheses X minus 5. That's my first term. Minus. Notice for our second term, my X minus 5s are going to cancel. 3 times 4, 12. Notice for my final term, the 3's are going to cancel. 1 times X minus 5 is simply X minus 5. I dropped the parentheses in this case because I'm just multiplying by 1 anyways. Okay, let's continue this. Tiana, would you go ahead and walk us through the solution for this problem? What would we do next?
I don't know, I might be wrong, but maybe distribute.
Yeah, trust yourself. Trust yourself. You're totally right. I'm going to go ahead and write what you get. 6X minus 30 minus 12 equals X minus 5. Keep going, Tiana.
Can we take the X from one side?
Sure. Is it okay if I bring the smaller one over?
Yeah.
Okay. So I have 5X minus 30 minus 12 is equal to -5.
And combine the 30, the -30 and -12.
Yes. So they're on the same side. We definitely want to put those together. So essentially we're cleaning up those like terms. Very cool. Keep going.
And can we take away the -42 and bring it to the other side?
Yes, which means we're going to go ahead and add that 42. Yes, absolutely. You're bringing the 42 over to the other constant, which is going to be really helpful because that essentially allows us to get our X term by itself. Last step.
And then divide.
Yeah, and then divide. We're going to divide both sides by 5. And voila, your solution set, thank you, Tiana, is that X is equal to 37/5. And you're done.
Do you always want it in fraction form? You don't want it in decimal?
That's correct. Yep, that is absolutely correct. For the most part, no matter what we're doing, if the original problem had decimals, then your answer can be decimals. Or if we're talking about, for instance, money, or maybe it specifies rounds to the nearest, whatever that might be. That's the only time. Every other scenario, if your original problem has fractions and your answer is a fraction, do not convert to decimals, okay? I would say err on the side of always leaving it as a fraction unless it specifically says round to the nearest whatever, or if the original problem has decimals in it, okay? That's a great question because sometimes, you know, we're not sure how to actually write it. Stick with the fractions, okay?
Okay, thank you.
You're welcome. Beautiful. For part C, what can X not be equal to?
0.
Yeah, awesome. So X can't be 0, right? Because if it were, error, undefined, it wouldn't work. All right, perfect. Someone else, what's your LCD? Shout it out.
X.
Yeah, super cool. Let's multiply each of the 3 terms by X. All right, someone else, what does this give me when we multiply every term by X?
X squared
Okay,
minus 5
beautiful.
equals 4x.
Yeah, excellent. Very nice. Someone else, where do I go at this point? How do I navigate this?
Set it to 0.
Yes, set it equal to 0. Perfect. So Oliver, would you agree that that means we're going to bring the 4x over? Notice Oliver said set it equal to 0. We have to in order to even think about factoring. I love this. So you recognize it was a polynomial equation. We got to do this. Okay, let's use some sets of parentheses. Let's go ahead and factor it. Who can tell me what my factors are? What goes in each of the parentheses?
X and X.
4.
X minus 5 and X plus 4. X minus 5 and X plus 4. Good. You were right with the X and X. And then we also, I heard like 2 answers simultaneously. And it was, and I did not mean to write plus 4. I meant to write plus 1. Happy Monday, right? -5 times 1, that gives us -5. And -5 plus 1, that gives us -4. We always do a quick check to make sure that we get the original polynomial. Just do a quick distribution to make sure that that works, and it does. So what are my 2 solutions? X is equal to?
5 and 1. Or 5 and -1, sorry.
Yeah, score 5 and -1. So let's go ahead and write our solution set. -1, comma 5. Those are my 2 answers. We lucked out. We didn't have to throw away any solutions because it didn't equal 0. So we were totally fine. All right, excellent. Let's go ahead and turn the page when you're ready and take a look at some problems that are just slightly more involved. It's not a big deal. You just need to, okay. When we look at the next set of problems, I want you to be like extra cautious because we're about to see problems with so many more moving parts. I just want you to just, you know, slow it down a touch, make sure you're moving very carefully and be cautious about how you're performing your mathematical operations. Okay, let's take a sneak peek. Did anyone have a question? Take a look at part D. What is my restriction? Go ahead and shout it out. What can X not be equal to?
-2.
Yeah, awesome. X can't be -2. Hopefully it won't be equal to that, but we don't know. All right, someone else, what's my LCD?
X plus 2.
Awesome. Take each term, just like always, and multiply by X plus 2. Beautiful. Someone else. What am I left with when I multiply by x plus 2?
X squared minus 5x equals 14.
Yes, x squared minus 5x is equal to 14. That was kind of cool, right? It just like quickly got rid of our fractions. Oliver, in this case, would say, set it equal to 0. So we're going to bring this over. We have x squared minus 5x minus 14 is equal to 0. Volunteer to tell me exactly what goes in these parentheses from left to right. What would you say?
X plus 2 and x minus 7.
Yes. X plus 2 and x minus 7. Excellent. This is just trial and error. So what are factors of negative 14 that combine to give you a negative 5? And that's going to be the negative 7 and the 2. When we continue this, we say, well, if x plus 2 is equal to 0 and x minus 7 equals 0, well, for this first one, I get that x is negative 2, and for the second one, I get that x is positive 7. Do you see what we got as our answer, but do you also recognize our restriction? What that means, everyone, is that we're going to have to throw this one away. We throw this solution away because we know this is an extraneous solution. If we accepted x equals negative 2, we would get an undefined fraction on either side of the equation, and that's a problem. We want to be really, really careful that we don't do that. This is why we look at the restrictions first. If we think about the restrictions first, then we're guided, right? And we could say, oh, all right, I have a restriction, so it can't possibly be that one, which means my solution is simply just a 7. It cannot be the negative 2 as well. Okay.
Professor,
Yeah.
I'm kind of falling behind on these ones. I don't understand. Like initially, how do we know that x couldn't be the negative 2?
Oh,
I'm totally
okay.
lost.
That's okay. What you'll want to do no matter what is always take your denominators and set them equal to 0. So check this out. If I take that x plus 2, the denominator, and I set it equal to 0 and I solve, this tells me that if x were equal to negative 2, that the denominator would be a 0, right? Also think of it as negative 2 plus 2 is 0. And we can't have zeros in the denominator. When we look back at our previous problem, for instance, this one, we had an x minus 5 in the denominator. X can't be 5. If x were 5, 5 minus 5 is 0. That's a problem. To figure out those restrictions, you always want to look at your denominators and say, what number makes this a 0? And that is what your restriction becomes. You see how I took the x minus 5 set equal to 0 and I solved? And I noticed, oh, so if x were 5, then that denominator becomes a 0, which is a problem. We can't let that happen. Does that help?
I've been doing pretty good up until this point. Like I'll just have to go back. It's not really dawning on me right now for some reason. But I'll have to go back. I don't want to.
Wait.
I don't want you to stop.
No. Can I ask one question, James? Look at part E. What number can x not be in this case?
1.
Yes. If x were 1, boom, this is 0, right? What about this side? X cannot be
negative 1?
Yes, perfect. You found the restrictions. Beautiful. You're absolutely correct. If x were a negative 1 in this case, boom, we have a 0. That's a huge problem. If x were 1 in this case, we'd have a 0, and that's a problem. So you right there just figured out what your restrictions are. When we go ahead and solve, if any of our answers are -1 or 1, we got to throw them out because we cannot have them as a solution. Okay, good, very good. Now let's continue with this
Just check that
idea.
it couldn't be the opposite of that. That's
Yes, yes, yes. The only time it would be a little bit more complex, so to speak, is like for part F. So here, X can't be 1, right? Here, we have to factor before we even decide what X can be. And then this one, X can't be, well, we have to solve it. So if we have 2X plus 3 equals 0, I'd have to subtract the 3 and divide by 2, right? So that means X can't be -3/2. So sometimes they get a little bit more complicated, so to speak. But really the trick is, James and everyone else who has this question, take your denominators and set them equal to 0 and figure out what those restrictions are. But
okay.
yeah, in this case, you're right. It's just definitely the opposite. Good. Okay, very nice. Let's go with Christina. What is your LCD for this entire equation? What do you think? What's your LCD for the entire thing? And actually, I have a better question. What are your denominators?
The x plus 1 and x minus 1.
Perfect.
Um,
Yep, it is weird because it's pretty big. It just takes it has a lot more moving parts, which is kind of what I was hinting at first. When Christina said your denominators are x plus 1, x minus 1, that is the LCD. You've got to have the combination of the two. So this is going to get a little messy. You want to write kind of small, or you can write this on a separate sheet of paper if you don't think you're going to have enough room, or on a tablet if you're technologically inclined, like Summer and Shane. So make sure you have whatever it is, you need enough space to do this kind of a problem. And we're gonna go nice and slow because I wanna make sure that this is totally understandable to you. Using the same process we did before, we're gonna divide out the denominator with that x plus 1, right? That's the match. I'm not even going to distribute yet. I just want to rewrite what I have so that it's clean. We want to be really careful with this. So I'm left with 3x minus 2 times x minus 1 equals. I don't have a denominator for my second term, so I'm just going to list this out. We have 4 times x plus 1 times x minus 1. Right? There's nothing that I'm going to cancel out. Then I have minus. And for my last term, I'm going to cancel out or divide out that x minus 1. Okay, we're moving
X plus
nice.
2, X plus.
Yeah, x plus 2, x plus 1, exactly. Okay. Gut instincts. What am I going to do first? Don't be shy. Shout it out. Gut instinct. What do you think you're going to do?
Distribute.
Yes, distribute. So let's start with this first set. We're going to distribute here. I like drawing the lines of distribution. I feel like it helps. 3x times x is 3x squared. 3x times a -1 is -3x. -2 times x is -2x. -2 times a -1 is +2. Very nice. What do I distribute next? I'm curious.
The 4 to the x plus 1.
Okay, I can definitely do that. I'm going to make one suggestion though, because in my 13 years of teaching, I've seen this mistake happen way too many times. My advice to you all, instead of distributing the 4 first, which is okay, by the way, But to avoid the error, instead of distributing the 4 first, distribute your sets of parentheses. Start here. I promise you're going to end up with the correct answer if you start with your sets of parentheses first. Okay, so we still have that 4. We're just going to bring that down. But we're going to multiply 4 by whatever we get here. So that means we need parentheses. X times x is x squared. X times -1, -1x. 1 times x, positive 1x. 1 times -1 is -1. Okay. Also notice we have a minus. And I have another 2 sets of parentheses. Make sure you distribute. Okay. But what do I need to use when I distribute everything in this last term?
You need a 1 before it.
I do, which means, check this out. So what Tiana's noticing is that we have a minus, right? And what she's automatically thinking about is that that's essentially like saying -1 times whatever we get inside. That's really, really helpful to know. We're essentially distributing that -1. So Tiana, thank you for that. That makes it very clear what we have to do here. So x times x, x squared. X times 1, 1x. 2 times x, 2x. 2 times 1, 2. We still have sets of parentheses, which means we still want to distribute. Okay, we have to distribute to drop all of the parentheses. It just so happened we had to use a couple of new sets in order to keep the integrity of the problem. I recommend to all of you, as you move through this left to right, combine like terms where possible. So essentially clean up when you can. So for instance, we have 3x squared. When I see -3x minus 2x, I immediately say -5x. And then we have +2. That's what I mean by cleaning it up. Make sure that you're tidying things up as you go along.
Would the next one just become 4x squared minus 4? Because
Yes. Yes, perfect. The 2 inner terms are going to cancel. And yes, this becomes 4x squared minus 4. Very nice. Keep going.
Then you just have x squared minus x squared minus 3x minus 2.
Yes, beautiful. Notice that 1x and 2x give us 3x. So when you distribute this in -1 throughout, that's what's going to give you the -1x, -3x, and -2. Very nice. We still have to combine like terms. So let's go through this process. 3x squared minus 5x plus 2. This is where it starts to pick up the speed, right? 4x squared minus x squared is 3x squared. We have a -3x. -4 minus 2, -6. Are you seeing what I'm seeing? What am I going to move first?
You can cancel out that 3x squared.
Yeah, you can.
And then you can put the 3x with the 5 to get a -2x.
Oh, wait, hold it right there. You're totally right. Let me show everyone what you're doing. So right away, Shane's noticing, this is Shane, right?
Yes.
Perfect. Shane's noticing those 3x squareds are going to cancel. You're left with -5x plus 2 is equal to -3x minus 6. So he's going to start just moving terms around and solving. Shane, you said add the 3x.
Yeah.
Keep going. It gives us?
-2x plus 2 equals -6.
Beautiful. And last, or second, I can't even talk. Keep going.
I would move that 2 over.
Yes. Let me just scoot this here so we can see what's going on. So we're going to move the 2 over. -2x is equal to -8.
5 by -2.
Perfect. And we get that x is equal to 4. Notice our restrictions. Our solution's 4, so no big deal. We don't have to worry about canceling it out. and saying that, oh, sorry, it's extraneous. It can't be part of my solution. And now we're finished. There were a lot of moving parts. I know this, but I'm hopeful that you found this actually to be quite manageable. We'll do one more problem before we go on break. How does that sound?
Perfect.
Beautiful. Okay, let's figure something out. First off, our first fraction, what's my restriction?
1.
Yes, so x can't be 1. So far, we see that. Let's look at this one. What can x not be?
Negative? No.
Yes.
-3?
Keep going.
X. What?
You were close. Let's take that, take the denominator, set it equal to 0.
Oh, -3/2.
Yes. So x can't be -3/2. And then this guy, 2x squared plus x minus 3, we got to factor this, right? So I'm going to factor this denominator for you. That way you don't have to go through the process of using AC grouping. If you factored this correctly, believe it or not, your denominator is 2x plus 3 times x minus 1. Go figure, right? Go figure that your denominator would be a combination of the other two. That's kind of a hint, by the way. Oftentimes with problems like these, to make it a little bit more straightforward, chances are if you did have to factor one of the denominators, it might be a combination of the other fractions. Just think about that. It's not always the case, but it may have one or both of the other denominators in the problem. So just kind of use that as a guide. Like maybe there's something in common here, and that's why I have this expression in the denominator in the first place. Okay. So our restrictions are done there. They can't be -1 and it can't be -3/2 because essentially they're the same as the other ones. Very nice. Kim, in this case, what is your LCD?
2x plus 3 and
Keep going. And what's the other one?
x minus 1.
Yes, perfect. Perfect.
My internet is cutting out, so I don't know if you can hear me.
Okay, okay, that makes sense.
Sorry.
That's okay, thank you. No, don't worry, don't worry. So your LCD is a combination, right, of the two, which is nice because that was already the case in our second fraction. So my LCD is going to be 2x plus 3 times x minus 1. 2x plus 3 times x minus 1. 2x plus 3 times x minus 1. Good. I would like you to move through this problem, and I would like you to find the solution. When you think you have the answer, go ahead and send it to me privately in the chat. If you have any questions as you're moving through this, send me a message. Good luck. How about we resume this and take a look together? I'm loving everything that is being sent into the chat, and we're kind of, trying this out together and talking through this, and I love it. I want you always to feel confident in that endeavor. Well, let's take a sneak peek, Oliver. Let's definitely just take a sneak peek. So we're going to divide out the x minus 1s. So that leaves us with 4 times 2x plus 3 is equal to, and then notice that the 2x plus 3 and the x minus 1 both cancel. So it leaves us with a 20. Then we have minus. Notice that 2x plus 3's cancel, but we still have a 3 and then an x minus 1. So we have a 3 and then we have our x minus 1. I'm not going to drop parentheses until after I distribute. So let's go ahead and actually do the distributive property here. So we have 8x plus 12 is equal to 20 minus 3x plus 3. Now we can clean up. So we have 8x plus 12 is equal to 23. So 20 and 3 make 23 minus 3x. And I'm just going to go through the process of solving for x. I'm going to add 3x to both sides. That leaves me with 11x plus 12 is equal to 23. I'm then going to subtract 12. So I get 11x is equal to 11. And then if I divide by 11, I get that x is equal to 1. Nope, it can't be. So because my answer was also equal to 1, I'm actually going to cross that out. And I'm going to note that this is an extraneous solution. So when you're thinking about, well, what do I write? Like no solution, you know, what happens? You could write no solution, or you could get fancy with it and simply say that x is equal to the empty set. That's called the empty set. Like there's nothing in it, okay? I can't believe I'm writing all weird. Good. What questions do you have for me on this guy? I know it was very involved. I know there were a ton of moving parts. And sometimes we just need more space. So if you have extra scrap paper, I would consider maybe trying to use that for some of these really big problems. So that way it doesn't get too cluttered. Okay, or too messy. Awesome. Okay, I don't hear any questions. Let's take a 5-minute break. I will see you back. Let's do 10:14. Okay, 10:14. See you in 5. Okay, so when you take a look at your next page, page 20, can you scope that out with me really quickly? I actually want you to look at page 20 and dissect this on your own at a later point, right? Like maybe after class or maybe a couple hours later today. Just give yourself some time to really digest all of the information that we're given. The reason being is that this page is hugely indicative of the differences in rational expression versus complex fraction versus rational equation. So they're all very different. Notice with this first one, we don't have an equation. So we have to think about how we simplify an expression like this. For our second one, we don't have an equation again, but it's a complex fraction. We have a fraction over a fraction, right? Essentially, that we have to figure out what's going on here. And then for part C, we're back to what we were just doing, which is solving a rational equation. So what I want you to do at a later point, and we can look at this together in tomorrow's class if you'd like, is I want you to do these on your own. And I want you to do this carefully. I want you to think about the differences in these 3 types of problems, because what's going to end up happening is you're going to see on your test, on your final exam, a combination of different problems, and you need to be able to know how to maneuver from one into the next, All right, so take some time later, not right now, of course, take some time later and dissect each of these. You can even write notes to yourself, like, what am I supposed to do here? Oh, what am I allowed to do here? And then for this last one, what's the best strategy for part C, right? I want you to think about that as you move through. And then we'll take a look tomorrow in class, okay? So do these later today at your leisure. All right, of course, as usual, we always have word problems, and we're right back to it, okay? Don't panic, these are actually pretty nice, especially if what we've been doing so far with multiplying by the LCD has actually been not too bad. So one number is 5 times another, okay? We are told the difference of their reciprocals is 2/5. find the numbers. Okay, I'm going to start this off for you. We still have the same relationship, right? I have one number, and I definitely have another number. We are told that one number is 5 times another. How would I write that algebraically? 5 times another.
So you have x
Sure.
or
So
5x.
5x, cool. Which means another number is just
X.
cool. There's your relationship. One number is 5 times another. Cool. That's exactly what this says. Now, here's the part that sometimes, well, here's the part that makes people feel uncomfortable. Notice it says the difference of their reciprocals is 2/5. All right, let's think about this one piece at a time. The reciprocal of 5x is 1/5x. The reciprocal of x is 1/x. Okay. Now, keep in mind the difference of their reciprocals is 2/5. So we want larger number, larger reciprocal minus smaller reciprocal is equal to 2/5. What that means, everyone, is that your equation is going to be, and I'll put it down here. Your equation is going to be 1/x minus 1/5x is equal to 2/5. You may be thinking, whoa, wait a second. Why didn't I write the other fraction first? Why didn't I write 1/5x first? Isn't that bigger? Think about this in a different way. Imagine if that number were 2, right? So we have 1/2. Well, 1/2, if we plug that in, is simply 0.5. But if x were 2, then this is 1/10, right? And if we take 1/10, we get 0.1. So this second fraction is definitely a smaller value than the first because the denominator is bigger, right? It's like 1 out of 2 pieces versus 1 out of 10 pieces. Does that make sense to everyone? Okay.
No.
No.
Okay. So because we know that our answer is positive, we have to just make sure we put the larger fraction first. So we can always play around with this idea. If we made x a different number, give me any number for x. Shout it out. Any number for x. 3. If I made x 3, then do you agree this is 1/3 minus 1/15? 1/3 is a larger fraction. 1/3 is 0.3 repeating. 1/15 is 0.06 repeating. So that means my larger fraction is 1/3. Another way to think about this is if you have the exact same pie, right? And if the first pie is cut into 3 slices, you're getting 1 out of the 3. That's a pretty substantial piece. But if you have another pie that's cut into 15 slices and you're getting 1 out of the 15, you're getting a tiny, dinky little piece that's definitely not satisfying. All right, just think about it like that in terms of fractions. Tiana, does that help?
Yeah, that makes sense now.
Okay, awesome. One thing you'll notice is if you accidentally switch the order, you'll end up with a negative number. And then you could just course correct. If that happens, you course correct. All right, very nice. LCD, who has it? What is my LCD? I have an equation, I should multiply by it, right?
$5x.
Yeah, cool. Take each term, let's multiply by 5x. I'm just gonna make a note here that your equation is 1/x minus 1 over 5x is equal to 2 over 5, just so that you have that. Sometimes Lumen says, hey, what's your equation? So we're going to multiply every term by 5x, just like we did before, because our goal is to cancel out fractions. So notice again, the x's are going to cancel. 5 times 1 is 5. And we're just going through the process that we've seen before. And that's a 1. And that's a 2x. And then we can simply say 5 minus 1 is 4. And then, of course, let's solve. And we find that x is 2. Keep in mind the goal of the problem. The goal of the problem was to find the numbers. What we always have been doing and will continue to do is we're going to look back at the relationship. Our relationship is that one number is 5 times x, and that another number is just x. So when we go and write our answers, we're going to say that one number is, what's the value? One number is
10.
10. That means the other number is
5.
what's x?
2.
2.
There's your answer. You just want to use the relationship. One number is 5 times x, x is 2, so 5 times 2 is 10. Another number is just x, x is 2, so you're done. 2 and 10. Those are your solutions. 2 and 10. Okay. Take a look at 18. The area of a rectangle is 80 square feet. I'm going to stop right there. First, we have a rectangle. Second, what's the formula for the area of a rectangle?
Times width.
Cool. So we see that area is equal to length times width. Okay, we know that the area is 80 square feet. So where it says area, I'm going to replace it with 80. So I've made a point that I took care of the fact that I know it's a rectangle. I commented on the fact that area is length times width, and I replaced area with 80 so that I'm keeping track of everything that's going on. Then it says determine the length and width if the width is 3 feet less than half the length. The width is, how do you write 3 feet less than half the length? Ooh.
So 1/2 x minus 3.
Yes, and instead of x, can I use L?
Oh, yeah, sure.
So 3 feet less than half the length. I'm going to use L for length, just so that when I solve, I know exactly what I'm solving for. What I'm going to do for my rectangle is label the sides. We know this is L. We know this is half L minus 3, and so is this side. Just so that our rectangle is dressed. Beautiful. At this point, we can now replace length with its expression. We see that length is just L. And we see that the width is half L minus 3. And there is our equation. All right, super cool. Princess, at this point, what would be our first step? So you're looking at this problem, how would you take a step forward? What would you do here?
Distribute.
Absolutely. Let's distribute that L and see what happens. So just so that you have it, let me grab my highlighter. Here is our original equation. I want you to keep that in mind. In Lumen, and I'm just going to point out that this was discovered recently. In Lumen, it may not accept 80 equals L times a half L minus 3. It might accept L times a half L minus 3 equals 80. So you may have to just put this on the other side, as annoying as that seems. Just keep that in mind. You may have to set equal to it instead of the reverse. All right, let's distribute. So we have half L squared minus 3L. Perfect. Where do we go from here?
That it equal to 0.
Yes, Oliver with the clutch, which is subtract 80, set it equal to 0. So we have 0 is equal to 1/2 L squared minus 3L minus 80. Okay, who can give me the next step? What should we do?
AC grouping.
We can, but I've never used half as my coefficient. And we use AC group when A is greater than 1. That's smaller than 1. How do we fix that?
Shoot, you're right.
How do I fix that? This is going to be a pesky little piece here. What strategy do I have that would allow me to get rid of fractions?
Could be multiplied by 2.
Yes,
Multiply.
yes, multiply by the LCD. Perfect. What is your LCD?
2.
Okay. Let's multiply everything by 2. This is a strategy you can use anytime you have fractions. So it gives us 0 is equal to L squared minus 6L minus 160. Cool. Think about what goes in the sets of parentheses for a second. Take a moment to think about what those factors have to be. What are factors of negative 160 that give you negative 6? Did you find it? What do you think?
Hence,
-16 and 10.
Yeah, negative 16 and 10, score. So we've got L minus 16, L plus 10. Double check L squared, 10L minus 16L, that's going to give us a negative 6L, and then negative 160. Excellent. So in our first set of parentheses, when L minus 16 is equal to 0, and actually I'll just write it out so that we recall the steps that we need to take. I don't want to just take it for granted. We find that L is equal to 16. When we subtract 10 in this case, we find that L is equal to negative 10. Because we are referring to the length of a rectangle, we know that the length cannot be a negative quantity. So I'm just going to throw this answer out. This is not possible. That's an extraneous solution. They are asking for the length and the width of the rectangle, which means we want to look right back here in our relationship. Okay, so length is just L, which is 16, and we know our units are feet. So we're going to say for the answer, we're going to say that the length is 16 feet. What's the width in this case?
Five.
Yeah, awesome, 5 feet. So we know that the length is 16, half of 16 is 8, 8 minus 3 is 5. Always use your relationship so that you can answer the questions being asked. What questions do you have for me on this page? Okay. Let's turn the page and check out some motion problems. These are essentially a blast from the past. We've seen these distance, rate, time problems before. Keep in mind, I'm giving you the formula at the top. Rate times time is equal to distance. That's actually really important for us to remember. Also recall from our past experience, we would set up our chart as, like, for instance, you know, person A, person B, and it doesn't have to be a person. It could be like a train or a car or two cars or whatever. And we always set it up where our columns were rate, time, distance. So that was the setup every single time we did motion problems back in 09-08. That was like our general chart or what it looked like. So what I want to show you is kind of a recap of that idea. Only this time it's going to be just slightly more complicated. It's not going to be too terrible. But I think as we progress through this problem, we just want to be careful of what are we trying to solve for? What are our unknowns? That kind of thing. Okay. Let me read the problem first, and then we'll set up a chart. A motorboat went 240 miles downstream with a 6 mile per hour current. When traveling the same amount of time against the same current, the boat was only able to travel 192 miles, right? Because it's harder. If you're going against the current, it's way harder than going with it, right? You could visualize that. Find the speed of the boat in still water. This is really important. I'm just going to underline this. Because I want to find the speed of the boat in still water, I'm going to use a capital B. If I ever saw that in this kind of a problem, I would immediately say, oh, B for boat. So B is the speed of the boat in still water. This is if the current is not impacting it at all. So that's the speed of the boat in still water. All right. I want you to think about the two scenarios that we are actually dissecting here. And I would hope you'd all agree that the motorboat was either going downstream or upstream. That's the difference, right? We're either going downstream or upstream. So I'm going to, instead of person A and person B, I'm going to write downstream, upstream, because I'm starting to create my chart here. I know that I have to have a rate, a time, and a distance. Okay, let's fill in the chart with the information that we're given, but be very careful. Put it exactly where it's supposed to go. Who can tell me where we would put the 240 miles? Where should that go in this chart?
Distance.
Distance, be more
And
specific.
downstream.
Perfect. Distance downstream. Okay, we're going to skip this for a moment. When traveling the same amount of time, that's actually really important. Traveling the same amount of time. In math, what does same mean?
Equal.
Ah, interesting. So I'm going to make a note of something. We're being told that the time downstream is equal to the time upstream. That's really very, very interesting. So I just want to make a note of that, because this is happening at the same, it happens at the same amount of time, essentially. Okay, now you're told, you're given some information, et cetera, and then you have 192. Where would you place 192 in this chart?
in distance for upstream.
Perfect. Okay. Here's the issue with the whole current thing. You're told a motorboat went 240 miles downstream with a 6 mile per hour current. What happens to the speed of the boat if it's traveling with the current? Slower, faster, what happens? All of you know this, come on.
Or faster.
It definitely goes faster. It's like, think about like if you were on a slide, if you were gonna slide down a slide, you're gonna go wicked fast. But if you try to climb up that slide, it's gonna be harder, right? So it's that same concept. In this case, when that boat is going downstream, the current is helping it. So it's giving it a boost. It's making it go faster. So when we think about the rate of that boat going downstream, it's only natural to think, well, you have a boat and you have the water. So together it makes a total combined rate. So check out the chart. Here where we see the rate for downstream, what we mean by that is the boat going downstream with a 6 mile per hour current. So the boat is moving with the water. That 6 mile per hour current gives that boat a boost of literally 6 miles per hour. So if the boat were only traveling like, 80 miles per hour, that's pretty fast, the 6 mile per hour current is helping it. So now it's moving 86 miles per hour. How do you think we would write it upstream if it's going against the same current?
B minus 6.
Yeah, perfect. That current is going to slow it down a little. It's not going to stop it, right? The boat definitely is moving faster than the current. Otherwise, it's going nowhere. But we do know that it's slowing it down because it's moving against. All right. Now here comes the interesting part. Time. We're left with time. So what that means is when we think about our formula, and I'm going to scoot this up here just so you could see it. If we have distance is equal to rate times time, but I want to solve for time, how would I do that? How do I get time alone?
Distance divided.
Divide.
Yes, yes. And I'm hearing somebody's mic that's totally correct. You're going to divide both sides by R, by the rate. So now you know that time is the same as distance over rate. That's a very interesting formula here. And this is something we're going to have to keep in mind. And of course, we can always, derive that ourselves. So time is distance over rate. What's the time moving downstream if you have the formula distance over rate? How would I write that?
$240 over the B plus 6.
Yes, and take a look at where I'm writing this. The time downstream. I'm also going to sneak it in here. It's just a little cramped. 240 over the B plus 6. Very nice. Distance over rate. We're going to do the same thing for upstream. Distance over rate. Distance over rate. Good. I'm going to go ahead and write that in the second half of this equation. Cool. And now we get to solve this. How should I solve it? Give me a technique.
The LCD.
Yeah.
B
What?
plus 6. B minus 6.
Perfection. Take each term, place it in parentheses. Let's multiply by B plus 6, B minus 6. Since that's our LCD. I'm loving this. I'm feeling like this is getting definitely easier. So we're left with 240 times B minus 6 is equal to 192 times b plus 6. And then, of course, we know how to solve this. I'm going to move through this in my notes without saying anything out loud. So I want you to work through this problem on your own and solve for b. When you're done, take a look at the video. Okay, and you can compare with my work.
Wait, Professor?
Yeah.
I got 1,092 for 192 times 6.
Let me try that again. No, I got 1152. Try that one more time. Did you get the 1152?
I put an 8 in.
Ah, okay. That's easy. That's an easy fix. How did you all do? Did you get B was equal to 54?
Yeah.
Beautiful. So what we're going to do now is just write down the answer. Keep in mind, B represents the speed of the boat in still water. So for our answer, we're going to say the boat or the boat's speed is 54 miles per hour. Always be careful with your units. I mean, it's possible it could have been kilometers per hour. In this case, it just so happened that it was miles per hour.
You know, technically it should be in knots, but
Oh, yes, that is true. That is true. Oh, man, and I know nothing about that. But I mean, it's the same concept. So if it were just labeled knots, then actually that's pretty cool. I should introduce that in a problem next semester.
oh, I apologize for everyone who was taking next.
Oh man, no, come on, it's fine, it's fine. Okay, beautiful. We do have 4 minutes left of class. So the only thing I want us to do, I don't even want us to solve 20. Okay, I don't want us to do that at all. What I'd like you to do is just to take a second. Let's read this problem together. And then I want us to fill in the chart. That's all I want. Okay, I just want us to fill in the chart. We don't have to do anything with it. So this says a car travels 250 kilometers in the same time that a truck travels 225 kilometers. Now you know who your characters are. If the speed of the car is 8 kilometers per hour faster than the speed of the truck, find both speeds. So let's start by setting up our chart. And that's all I want to do before we continue this tomorrow. We will finish our notes tomorrow. Okay, so make sure you have Unit 3 notes printed out as well.
Ready to rock.
Yeah. So rate, time, It's always the same. It's always the same distance. Okay, I'm going to guide you. So you just follow along. Don't say it out loud, but where would you put the 250? Don't say it out loud. Place it in the chart. Okay, you should have placed the 250 in the distance for the car. Okay, where would you place the 225? Don't say it out loud. Go ahead and throw this into the chart. Okay, you should have placed this in the distance for the truck. Notice that distance is in terms of kilometers. I'm going to write kilometers right above it, just so that we keep that in mind. You then told the speed of the car is 8 kilometers per hour faster than the speed of the truck. How do you write 8 kilometers per hour faster than the speed of the truck? Word for word interpretation. How do you write that? And now someone share. How do you write 8 kilometers per hour faster than the speed of the truck?
T plus A.
Yeah, you said 8 plus, you said A?
8.
Okay, beautiful. So we're gonna write, and actually, is it okay with you if I write 8 kilometers faster than, and then I call the speed of the truck like capital T? Is that okay?
Yes.
Okay. So the rate of the car is 8 plus T, which means the rate of the truck is just T. Okay. How do you write time here for the car? What do you place right here in this spot for the time that the car took? Who has
Would
this?
it be just a normal T?
Actually, we have to think back to our expression. What do we know about time?
That
Oh,
would
so
be
would it? No, it's okay. You can do it.
250 over 8 plus T.
Yes, 250 over 8 plus T, because time is equal to distance over rate, something to keep in mind. For the truck, we would write
225 over T. Sorry, I was writing.
That's okay. And then we're going to pause right there. You can go ahead and solve this on your own if you would like. Remember or recall from the word problem that you're told that this happens at the same time. I think that's all you need in order to be able to set up the equation and to solve. But we will finish this tomorrow in class. So excellent work, everyone. This was absolutely fantastic. I feel like this is going really, really, really well. Make sure you continue to practice. Make sure you're working on that homework too. As always, if you have any questions, don't hesitate to ask. I will be staying right now. So if you have any questions that you'd want to go over with me, even if it's in Lumen, let's take a look right now. All right. But I'm going to stop the recording. So everyone, I will see you tomorrow. Enjoy the rest of your day. All right.
You
See
too.
ya.
Bye-bye.